Greetings and salutations, everybody. This is Jacob. Okay, so how on earth do we go about unraveling this problem right here, you ask? It seems baffling. Worry not, my friend. I'll walk you through this problem step by step. I'll break this problem down so that even the average person walking the streets can break down in tears, marveling at the beauty of this problem, my friends. Oh yes, you better believe it. So let's get the ball rolling, shall we? Okay, so the problem is asking us to find how many 6-digit numbers there are that have exactly 4 distinct digits. Keyword exactly. One such number that fulfills this criteria is 630,400, for example. It has the 4 distinct numbers in it, 0, 3, 4, and 6, correct? So is 571,937, for example, one of the numbers that we're considering? No, because it has 5 distinct numbers in there. 1, 3, 5, 7, and 9. Correct? So I want to make it abundantly clear of what I'm asking in this problem before proceeding any further. And if you had some other idea of what the problem was asking and still want to give the problem a shot, then pause the video here or come back to it later if you want to. Okay, so now that we've clarified what the problem is asking, in order to gain an intuitive grasp of this problem, first let's take a look at the 3-digit scenario, and we'll come back to the 6-digit scenario. So how many numbers between 0 and 1,000 are there that have 2 distinct digits, for example? Let's list all such numbers up to 100 for starters. It's 001, 002, 003, 4, 5, 6, 7, 8, 9, 10, 11, 20, 22, 30, 33, 40, 44, 50, 55, 60, 66, 70, 77, 80, 88, 90, 99. Correct? So 27 numbers total from 0 to 99. How about from 100 to 200? There are 100, 101, 110, 112, 113, 114, 115, 116, 117, 118, 119, 121, 122, 131, 133, 141, 144, 151, 155, 161, 166, 171, 177, 181, 188, 191, 199. Again, there are 27 such numbers in this bracket as well. And I'll bet my house there are 27 in the next 100 number batch as well, and in the next, and in the next. So the total amount of such numbers from 0 to 1,000 is 27 times 10 equals 270 possibilities. Okay, so how do we come up with this number without actually having to list them out one by one? Using the sum and the product rule of enumeration. So since we have 3 digits, let's look at these 3 slots right here. For the first slot, how many possibilities are there? There are 10 distinct possibilities, right? 0, 1, 2, 3, all up to 9. So we put 10 in there in this first slot, 2 slots left. Okay, so what are the possibilities for the second digit? Here's where the trickiness starts, my friends. Let's say the second digit is a distinct number, different from the first digit. So since we have 10 possibilities for the first number, now we have 9 possibilities for the second digit. It's like we're drawing from a pool of 10 balls without replacement. So we drew 1 ball in the first digit, and now we're left with 9 balls to pick from. So far we have 10 times 9. Now we go to the third digit. What are the possibilities here? Since the first and the second digits are distinct numbers, and the total 3-digit number has only 2 distinct digits, then the third number has to be a repeat of one of the first 2 numbers. So there are 2 possibilities for the third number. It's either a carbon copy of the first number or carbon copy of the second number. So now we have 10 times 9 times 2 equals 180. But we're supposed to get 270, not 180. Not so fast, we're not done yet. But what if the repeat number is in the second digit? We didn't take that into account, did we? We then have in this scenario, we have 10 times 1 times 9. Because if the repeat is in the second digit, then there's only one possibility, that it's a carbon copy of the first number. So there's only one possibility, 10 times 1 times 9. So the total number of possible numbers that we have for 2 distinct digits from 0 to 999 is the sum of the possibilities where the repeat number is in the second digit, plus the possibilities where the repeat number is in the third digit. And the repeat number can't be in the first digit, since by definition it's the only number, correct? Does what I'm saying make sense so far? I hope it does. Okay, moving on. So we have 10 times 1 times 9 plus 10 times 9 times 2, which is 90 plus 180, 270. Voila. We get the same exact number that we got by listing the numbers one by one, correct? Okay, so how about the numbers that all have distinct digits from 0 to 999? For the first slot, you have 10 possibilities, like in the previous example. In the second slot, we have 9 possibilities. In the third slot, we have 8 distinct possibilities. So 10 times 9 times 8 equals 720. So in other words, we only use the product rule when we're only dealing with distinct numbers, because in the first slot, we'll always have 10 distinct possibilities. In the second slot, we'll always have 9. In the third slot, we'll always have 8, etc. The possibilities, in other words, are fixed when we're only dealing with distinct numbers, my friends. In the first scenario, we had to break things down using the sum rule because we have different possibilities based on where the repeat number is located. So 270 plus 720 equals 990. But there are 10 numbers missing, you say. These 10 numbers that are missing, they're actually the numbers that only have one distinct digit, 000, 111, 222, etc., up to 999, 10 in total. So we have 1,000 numbers in total. So we have everything accounted for. Oh, yes. So now that we've armed ourselves with some intuitive understanding of this problem, let's go back to our 6-digit scenario and try to make heads or tails of it. So we have 6 digits total, but only 4 distinct digits. That means what? It means we have 2 repeat numbers in there. That is, numbers that repeat one of the digits that came before it, from left to right. There are various ways we can distribute these 2 repeats throughout this whole number, obviously. So there are 5 available slots for the repeat numbers, correct? And we have 2 repeat numbers. As we said earlier, the first number can't be a repeat by definition. So there are 2 repeats we can choose from and assign each of them one of the 5 available slots. And so we use a combination formula to figure out how many ways we can distribute the repeat numbers within the whole number. Do you recall the formula? It's NCR, or N over R, in parentheses, equals N factorial over R factorial times N minus R factorial. So N in this case is 5 and R is 2. So we have 5C2 equals 120 over 12, which is 10. So we can distribute these repeats in 10 different ways throughout the number. So since this number isn't actually that big, we can list out all the possibilities one by one. It's the repeats in the slots 2 and 3, 2 and 4, 2 and 5, 2 and 6, 3 and 4, 3 and 5, 3 and 6, 4 and 5, 4 and 6, and 5 and 6. Correct? So the total number of passwords with 6 digits and 4 distinct digits is going to be this sum here. So now what do? So now we figure out the possibilities for each summoned using the product rule, starting with n, 2, and 3. Okay, so the number of possibilities for the first digit, in this case, is 10, as we said before. What about the second? The second is a carbon copy of one of the previous digits, and the only one is the first digit, so there's only one possibility, correct? So 10 times 1. What about the third? Here we have one possibility again, since there's only one unique number in the first 2 digits. So 10 times 1 times 1 so far. How about the fourth? The fourth is a unique number, so there are 9 possibilities left for unique numbers. How about the fifth? 8 possibilities. And the sixth, 7 possibilities. Correct? So we have 10 times 1 times 1 times 9 times 8 times 7, which is 5,040 possibilities for this first case. Moving on to the next case, n of 2 and 4. So we have 10 possibilities for the first number, 1 possibility for the second. Now the third is a unique number, so we have 9 possibilities for the third number. The fourth is a repeat. So far we have 2 unique numbers before the 4th digit. So we have 2 possibilities for the 4th digit, and the rest are unique numbers. The 5th has 8 possibilities, and the 6th has 7 possibilities. So we have 10 times 1 times 9 times 2 times 8 times 7, which is 10,080 possibilities. Moving on, n of 2 and 5, 10 possibilities for the first, 1 possibility for the second, 9 possibilities for the third, 8 for the fourth. How about the fifth? The fifth is a repeat, and so far we have 3 unique numbers. So we have 3 possibilities for the fifth number and 7 possibilities for the sixth. And we multiply these numbers and we get 15,120. Moving on to n of 2 and 6, here we have 10 possibilities, 1 for the second number, 9 for the third, 8 for the fourth, 7 for the fifth. Now the sixth is a repeat, and so far we have 4 unique numbers that came before it. And so there are 4 possibilities for the sixth digit. And we multiply all these and we end up with 20,160 possibilities. And we use the same logic for the rest of the cases. And the rest of the cases are as you see here. And so now that we've gone over each case, now we add up each case, as we said before, to get the total number of possibilities. And all this adds up to a grand total of 327,600. And that's all she wrote, my friends. That's your answer. 327,600. I can't say that's an intuitive answer, because if you multiply 999,999 with 40%, since we're using 60% less digits, then you end up with 400,000 roughly. And so we have less possibilities than what our intuition would expect. Such problems are a gold mine, my friends, because if you don't encounter problems that fly in the face of human intuition, then you can't expand your intuition, my friends. So that was a fun little combinatorics puzzle, wasn't it? I hope you liked it. I carefully selected/constructed this problem because I think it expands our understanding of combinatorics in a deep way, of enumeration and counting things in general. Oh yes, there's more than one way to skin a cat, and this is one such problem. So let me know in the comments if you solved it another way. So did I select this problem or did I construct it? A little bit of both. I took a similar looking problem I saw somewhere else and I tweaked it a little bit. In fact, most of the problems you see on this channel are of this category. In fact, very few problems I present are unmodified problems I saw somewhere else. Well, not that few, but around say 20 to 30%. So yeah, combinatorics, man. If done correctly, this field of mathematics, it'll kick your teeth in from time to time, but it'll also skyrocket your understanding of math in general, like nobody's business. It's a deeply rewarding field. So let me know down in the comments what you think. Smash those buttons, like the world is ending. Shoot a puzzle suggestion my way, and I'll see you guys in the next video. Take care. Bye-bye.